All right, so what are we doing? All right, so I'm going to go back and forth between our slideshow and then some practical stuff. So today we're talking about machine learning. What are we going to do? The topic of this, we're going to define machine learning. We're going to go over some real world examples of machine learning. And then we're going to look at Tensorflow to develop a simple machine learning algorithm. So, what is machine learning? Textbook Oxford defines machine learning as the use and development of computer systems that are enabled to learn and adapt without following explicit instructions by using algorithm and statistical models to analyze and draw inferences from patterns and data. That's the Oxford. So, like practically, some way to think about it is finding patterns and data to solve problems that it wasn't explicitly programmed to do. What can we do with machine learning? Usually, machine learning will perform better on tasks over time throughout training. And while we're here, what are we defining training as? Is feeding model to the data. If the model gives better results over time with the same algorithm, it's said to have learned. What types of machine learning are there? So we have prediction, uh, prediction type. We're going to go over a type of kind of prediction type today, where this would be people who come up with algorithms for trying to predict stock markets, but even the biggest hedge funds and the largest things with so many confounding data points, it's hard to find accurate prediction models for something as intricate as the stock market. Classification would be image recognition, where the computer looks at patterns of pixels and tries to find or looks at data of pixels, tries to find patterns to identify images. Customization targeted ads. These are the ones we see probably the most on our phones, where we get our search history, looks through different search histories, and tries to target specific stuff for you directly based on what you might like or what you've already uh, done. It's kind of a classification with a twist. Translation is inputting some language and its equivalent to another language. It's difficult when it's not direct. Languages like Chinese, or not really Chinese, but uh, Mandarin or the other dialects of China are hard to go to English because sentence structure and things like that. So and the another one would be game AI. This is the one I would probably have the most experience with, being like a esports coach. Things like this, chess, Go, produces strategies on highest chances of winning. Some really interesting stuff with game AI. Deep Blue versus the newer chess learning algorithms or machine learning. Um, Machines learn better from playing against themselves, they found, than going over data from famous chess players. So there's been a lot of advancements in chess game AI since Deep Blue and the whole anecdotal like Bobby Fischer stuff. Or no, he didn't play Bobby Fischer. He played somebody. I have to look that up. All right, so this would be personalization. It's more of the targeted ads, and then translation is what we talked about. This is what Google has done with their machine learning for their translator. So, like, say this was Chinese and this was English, Google had developed it's easier to put it into this middle language uh, and then transfer from there. So, on their own, they developed like this intermediary coding only language to translate different things. And the more it gets better and better every year. So those are the ways that we do machine learning. Here are some of the types: supervised, unsupervised, and reinforcement. But they all have something in common, which would be pattern recognition. Just some examples of supervised and unsupervised with some visuals. Supervised learning, they tell you what it is and what it's not. Duck, duck, not a duck, not a duck. Supervised learning gives you a predictive model. Unsupervised would be, you know, just showing everything and then letting the computer find the patterns. So feeds and inputs and outputs, these are supposed to be labels, or another word for outputs. Clear end goals, such as a number to predict a category. During the training, the model tries to match its outputs to the labels by modifying internal values. So we're going to go over how to build a simple machine learning linear regression model, and we're going to use some different data management type applications, Anaconda, Tensorflow. But what are the steps? We can use machine learning to solve problems, but we got to know what the model what should we use it for? We have to gather and format the data. We're going to have to build a neural network. We're going to train the model. We're going to test it, evaluate, and we're going to refactor, gather more data. So we're doing a very basic, simple one just to show you some tools that people use to do machine learning models. So we're going to not collect and gather our own data, but with a lot of experience and a lot of more practice, you could probably go off on your own and develop. So TensorFlow is a lot of pre-implemented algorithms, model structures, nose types. It's good because I think it's open source, but it's free. And then you import TensorFlow into any Python file. So, when we're naming stuff, TR whatever you want, TR floats, TR strings. Python's a really easy to use coding language. So, if you have experience with that, it's easy to, transfer. So really basic. We're going to go over this stuff in a second, but Anaconda Jupyter. Anaconda is, another source, and Jupyter Notebooks. And then this is just the basic how Jupyter runs. It's web-based. You would highlight each one of these cells, run the cells, and this order shows you the number in which you ran the cells. And just like importing, I don't know, from back in our classes on SQL, it looks, import TensorFlow as, right, similar, import something as, so similar setup. So how can we use TensorFlow to build, train, and test machine learning? Linear regression, that's that fitting a line on a scatter plot. So we're going to fit a line through data to minimize the average distance between all the points. It's best fit. This is like a predictive model. So just looking at it, if we look at this line, if we carried it over to 70, we'd be somewhere in the, you know, 14 range. It's got one dependent and one independent variable, and our model is just going to be a single layer, simple, super simple model. How does linear regression work? Scatter plots would be usually with one axis relying on the other axis. X-axis is usually. So then the line runs through the data, roughly through the middle points with even numbers above and below, and then errors by totaling the absolute values of the distance of each point's y value and the line at the point. So we're gonna, like I said, we're gonna go over this a little bit more, but these are the biases and the intercept points. This would be just a standard, line, right? That's not how data usually comes. So, we're going to map it out as a scatter plot by adding some noise and the random numbers. And then if we look, we have more of a scatter plot with some distribution. And then we're going to put a line of best fit on this scatter plot after running a bunch of tests to try to get a learning algorithm to work. So what are the drawbacks? There's always ethical concerns. How much advantages is there to trusting algorithms? Some of the things we discuss, like pre-crime and predictive crime and those type of things. It's ethical, and then a lot of these kind of things overlap. So lack of data also kind of in different situations combines with ethical concerns. So recently, there's been a lot of machine learning when it comes to breast cancer and identifying scans, but the data that's collected is mostly of white women, and then statistically African Americans are 42% more likely to have that type of cancer. So with the lack of data and the machine learning, the data is the machine's only as good as the algorithm and the amount of data it gets. So with the lack of that, it's kind of almost ethical and lack of data concern at the same time. Lack of interpretability. The computers are really good at finding patterns that we might not see, but if we aren't able to identify what those patterns means, then those are some other problems. So the references, the dictionaries, we have the Zenva Academy, where we're going to go through how to do some of these things in real world scenarios, and then the limitations that we had from this article and the bullet points explained in more detail. So, real quick, we got Anaconda, right? So this is we've used RStudio in other classes. I've used Spider for Python coding, and VS Code is those. But today we're using Jupyter. Jupyter is interactive and it's web-based, and you could import different things on there. So if you wanted to uh, install TensorFlow, which is that thing with the pre-done packages, you would, go to environments on Anaconda, base root, open the terminal, and then, conda install TensorFlow as TF, right? So that's sometimes that's tricky for people when they make the new environments in the beginning. Just using it seems like there's a lot of different stuff going on all the time. So that's one little hiccup if you don't have it. You could also install it through the straight up command with PIP, but uh, I think it's easier to go through the conda terminal to install things. All right, so TensorFlow, right? Right now I have some stuff running. This is how it's set up. I'm inside my documents, and these are examples, and then we'll just go through some basic coding. So, just like we did R before, RStudio, there's always like pre-done packages that makes it a little bit easier to get these kind of plots, right? So we have our, basic package of NumPy and Matplot and TensorFlow. Then we just did some random numbers from 0 to there, and then we added some noise on that axis, and then we kind of made a scatter plot. So our machine learning model is going to, you know, run a bunch of epochs to try to get a line of best fit for this scatter plot. Um, you know, I don't know. So at the beginning, there could be lines there, I don't know, there. So it is kind of difficult. The lines, I mean, if you wanted to, you could adjust these to make them finer, but I guess real world data might be messy too. So hopefully that's like the whole purpose. But it seems like there's a lot of different places where you could put a line of best fit on this model to begin with. So this is just if you know Python or divide or self. We're gonna call it self. We're gonna have our variables. Um, we're gonna multiply them by the biases and run them. We're gonna do. You could put everything in the same cell and run it, but sometimes different cells, and you could run it whenever you want, right? And if you wanted to get rid of it, you could cut it out. But so we defined a couple variables. We're trying to find the loss. We're trying to train the model to you know get better. So this would be our model training and epochs in range. So epochs are like how many times it's going to run this model. And then I know like you might think that like the more you run it, the better or more accurate, I guess it would be. But um, throughout like these training videos, it's kind of been explained that there is a point of diminishing return. So if you did like a million training things, you're not going to see much of a difference between the first 100 and the next 900,000, right? It's just going to take more time. And so but if you do change different things, epochs, whatever, so we made a class, the model, we're going to print out how we're doing based on running this training program. And as you can see in the beginning, we're like 700 off. As we move down into the different iterations, it looks like near 35. I mean, we get big drastic changes down to actually, I guess, 21. And then small, and then it seems like the last 30 to 40 iterations don't have much significant change. All right. So then if we look at, where we are, we printed that, we printed the bias. If we go back to our original 2.5 or 5/10, and we're at 207 and 6. So that's actually pretty close, right? Uh, to where we were to begin with. Just in general, if we plotted out our line of best fit, it's pretty, and then we put the original on top of it. We have a pretty kind of close line where um, the points seem to run through. And with this whole, linear regression models, linear is like a line, right? So we should be able to predict 5, 6, and 7. Now, in this, we just set up random numbers, random integers to kind of test our model. But with documentation on different places, you can put in your own or collect your own values. This is just to show you the basics of, like, maybe TensorFlow, what it does, Anaconda, how to organize, and then how to use Jupyter notebooks to run the cells, cut the cells, uh, to pretty much, you know, be able to run these machine learning algorithms. Uh, Overall, in conclusion, it seems like machine learning and algorithms, there's like no limitations. The only limitations would be, you know, how much data you can collect, how accurate the data is, and are you able to see the patterns or uh, what you could use them for. But overall, it seems applicable in so many different ways from, you know, it's going to be even bigger for, it's already started in advertising where we're getting, strategic ads given to us, and then image recognition. I think it's really important the way it's going with medical thing and analyzing, possible breast cancer patients. But that brings up some of the limitations where most of the data collected are going to be uh, right now white women instead of minorities, but there could also be it could also be access to insurance thing. So those might also be coupled with like insurance type problems, who has access to the healthcare.